for the next topic, I'd like to talk about a little bit more, expand the ideas about the probability distribution. So we will just introduce this notion of expectation and the integral, which is the kind of main notions that we want to talk about, like expectations of like some events or like integration in this notion of the group ZP. So like for example, this could be like a starting example that we have this what would we have like function f from ZP to I could take this maybe on the reals, and the function has this following property that this is defined to be 1 and minus 1 if t is even and t is odd. So that's a function that we could like understand, would like to know that what's the like for example the expectation of this function. Like for example this is basically like what I would like to think about, like a notion in probability you could call a random variable. So what would be the expectation of an event of that? Let's say you choose a random number from the group ZP, and then whether it's even or whether it's odd. So what's the probability, like the expected like evenness or oddness of a number that we could have. So how to define like this like expectation of the function, this expectation. Or we could also think about what to define something called an integral, what the notion that we will want to use. So this is like something called integral. So for this purpose, I start from this definition 2.17, and here we'll just define this formally. So we define if we have any function, if f is a function from ZP, and actually we put it all the way to complex plane. So we will end up seeing later on that we actually need complex valued functions. Just if you kind of maybe forgotten something about complex numbers, could maybe revise a little bit on what they are and some basic properties of them. But here just take a complex valued function, and then the integral or expectation of f with respect to a probability distribution mu from ZP to 0, 1 is just defined to be this number mu of f. I use this notation a lot, mu of f, and you sum over the group of ZP, ZP, and you take the value of the function at this point t that you are summing over, and then you take the value of the probability distribution at this point, mu t, and you end up to this notion of the integral of the function. And this is basically a sum, so it will be a number in the complex plane again, because you're basically summing complex numbers and multiplying them with some real coefficients, which are these weights. So this will be a complex number. So the notation that people use, and I might use in this course sometimes as well, is that you use you define this also this kind of integral d mu, and also sometimes use this notation of expectation. You put subindex sometimes to highlight that it's the measure mu. So it's all the same notation that we use here. And for those who are in the audience who maybe are more familiar with analysis, this looks maybe a bit sketchy that you're basically defining integral to be a finite sum. I agree with that. That's really like a bit weird maybe to think about it as an integral. But the idea is that somehow when you take somehow the p to infinity in this definition, you had more and more group elements. These kind of sums that you obtain start to look like these kind of, for example, like Riemann sums that you might see in the definition of Riemann integral or something. So, and many times when you compute Riemann integrals or integrals in general, you usually need to study their definition, the approximations, which are finite sums. So this is just more like a discretized version of the notion of integral. It's just a convenient to use the same notation that in the later on, that if you would study more complicated groups or something which are like continuous groups where the measures, these probability distributions can't be defined so simply, then it's easy to see where you actually are using integration. You're just using integral in those notions. But most of the time I will use this notation μf to be able to define everything properly. And let me give you an example of this. So just a very simple example. First example, that if f is this indicator function of this, so remember indicator function, I don't know if we've seen this, but it's defined to be just 1 and 0 if t is in A and if t is not in A. So this is some subset of ZP. You can define an indicator function with this notation. And what is now the integral of this? So this mu are 1a. By definition, if you look into this definition of summing over this, then you're just basically summing t in zp of indicator function a of t and then mu of t. Then what you obtain, if you sum this over, this quantity is as you said, it's 0, 1 if t is not is in A and t is not in A. So basically you're multiplying zeros at those other points. So that's why you can actually write this as a summation of just over the points in A. And that becomes actually the definition of mu of A. So that's why one of the reasons I wanted to use this notation mu of A, because now you see that this matches with the idea of probability. So if you take the integral of the indicator function or expectation of this 1 of A d mu, or well, it's the same notation as expectation of 1 of A, then this is just the probability of the event A happening. So that's the kind of like, it's integral can expands this kind of notion. And the other example I wanted to give was what I talked about, the even and odd examples, was this function ft, which is the 1 and minus 1 is t is even and t is odd, and assume p is even. Let's assume this for convenience in this notation, so that basically e.g. p is 2 or 4 or 6 and so on. So it's one of those numbers. Then what happens is that the integral, I don't know what could take, let's study the probability distribution to be the uniform distribution. So this is the uniform. If you remember, the uniform distribution was defined to be lambda t is 1 over p for every t in Zp. Then what is the integral or expectation? So here we use this notation lambda mu, so this is, remember, the integral notation. So that's the summation of t in Zp, and then you have f of t, lambda t, and you obtain, if you just compute this outright, you just get that, because if you take the circle, this is basically saying that when it's an even number of points in the circle, then there's actually exactly p over 2 even numbers and p over 2 odd numbers. So there will be p over 2 times that this value is actually given by this value is given by -1, so there will be p over 2 when it's given by 1, and in those points we have the probability 1 over p. This is always 1 over p for every t, and that's 1 or -1 depending on whether it's even or not. And then you have the p over 2 values where it's equal to -1, and that's the probability of 1 over p. So that's when it's I think I defined this to be when it's even and when it's odd, and that's the number of times, and that's also the number of times. So what you end up into the actual number, you end up that these cancel out, so you just get into 0. So the expectation of a number to be either odd or even is 0. So the value of this function is basically 1. It's just saying that there's equal number of the proportion in the step of measure is roughly the equality of the thing. And then as a last thing I maybe want to talk about before the end of the lecture is this idea of maybe I could I think that's maybe the last example I wanted to talk about for now.